Bismillahirrahmanirrahim. Assalamu alaikum, students. Now, in last lectures, we were discussing applications of Gauss's law or theorem. Today, I will continue with that because that was incomplete. So, I write here continued. Last time, we were discussing fifth application, and that was related to a charged isolated conductor. So we are in this application. One result or property of this charged isolated conductor we already derived or established it using Gauss's law. That result was, I will state that to remind you, an excess charge placed on an isolated conductor moves entirely to the outer surface of the conductor. None of the excess charge is found within the body of the conductor. So we said if we have, let this be thread, and this my thread. And we said if I have a lump of copper, which is in cross section showed in this diagram. Now I charge it with some charge, positive charge Q. We claim it that this charge lies on the outer surface of the conductor. None of it is found within the body of the conductor. And I already emphasized, and I'm repeating that current carrying wire is not an isolated conductor. Isolated conductor is that conductor which is charged and is left isolated from any charge source. So there is an electrostatic situation. All the charge in it are at rest. Then we proved this result that all the charge lies on the outside boundary. None of it is found within the body of the conductor. But we took a Gaussian surface just inside the actual surface of the conductor. And then we said, since there are no currents inside the isolated conductor, electric field inside it must be zero. And then from that, we showed that if we take a Gaussian surface just inside the actual surface of the conductor, apply Gauss's law to it, there will be no flux through the surface. Therefore, there is no charge inside my Gaussian surface, but there is charge on the isolated conductor that must lie outside the Gaussian surface and therefore the actual surface of the conductor, right? So that was result A. Now I move to result B of isolated conductor. Right now I have an isolated conductor. All the charge is on the outer surface. The question is, second result I will put it like this. Creation of a cavity will not affect the distribution of charge on the actual surface of the conductor, right? I'm saying if I create a cavity inside this isolated charged conductor, that is not going to affect the distribution of this charge Q on the outer surface. That means creation of gravity will not disturb this distribution, right? Now, how to prove that? Let me show a diagram. So now I have this my thread. I'm saying proof. Now I have a thread, and I have this lump of copper. It is charged. Q is excess charge, right? Now there is a cavity. There is some cavity. This cavity, we have scooped out some portion of the conductor out of it, right? Now let me write first here. It is cavity, right? So consider a Gaussian surface lying inside the body of the conductor, lying inside the body of the conductor and enclosing the cavity walls, right? Let me show that. This is this blue colors I have shown it in broken line is my Gaussian surface. Is my Gaussian surface. You already know that electric field inside the body of the conductor is 0, since there are no internal currents. So we take the Gaussian surface, which is lying inside the body of the conductor and enclosing the cavity walls, this boundary, this cavity wall. Now, applying Gauss's law. Applying Gauss's law, which says net flux through the surface is Q, I will write here, Q in by epsilon naught in order to distinguish this charge from the charge on the surface. So here Q in is what? Charge inside the Gaussian surface. Charge inside the Gaussian surface. Now, since electric field inside the body of the conductor is 0 and my Gaussian surface is lying in the body, so flux is 0. So it is 0 implies what? Implies Q inside is 0. That is, there is no charge inside the Gaussian surface, right? Now, cavity walls lie inside the Gaussian surface. Therefore, there is no charge on the cavity walls. Now, why I'm talking of cavity wall? Let me make that clear first. See, if this charge, let me show it here. Try to understand it. This is thread. This now copper. Let me use another color. Now there is charge on the surface Q. Now I am creating cavity, right? How can charge move within the body of the conductor? Either the electrons from the surface of the actual surface of the conductor will move to the cavity walls, or from the cavity walls, electrons will move. For example, if an electron moves from the surface to the cavity wall, one electron, so this charge on the surface will increase to plus E, because E is the charge on the electron, because one electron will disappear from the surface, it will appear on the cavity walls. On cavity walls, minus E charge will appear. Total charge in the conductor is still Q, because Q plus E minus E is Q, right? If two electrons move from the outer surface to the cavity walls, charge on the outer surface will become Q plus 2E, because two electrons will move, therefore 2E positive charge will appear on the surface, but 2 minus E minus 2E negative charge will appear on the cavity walls. Or reverse can happen. If electron moves from the cavity wall to the actual surface of the conductor, then here what will happen on the cavity walls, plus E charge will appear, and here Q minus E charge will be on the outer surface. Total charge on the surface in the conductor, sorry, will still be Q. So I am saying, when we say creation of a cavity wall will not affect the distribution of charge on the actual surface of the conductor, we are in other words saying that if we create a cavity, there will be no charge creation on the cavity walls. Because if the charge distribution changes, the distribution of charge Q on the actual surface changes, then there will be certainly creation of charge on the cavity walls, right? If electrons move from surface to cavity walls, then there will be negative charge created on the cavity walls. If electrons move from cavity walls to the outer surface of the conductor, then positive charge creation will take place on the cavity wall. So if we have to prove that creation of a cavity will not affect the distribution of charge on the actual surface of the conductor, it is sufficient to prove that there is no charge on the cavity walls, right? So that's why I'm saying this. So we said, applying Gauss's law to our Gaussian surface, it lies within the body of the conductor. There is no electric field inside the body. So flux through the surface is zero. Q inside is zero. And there is no charge inside the Gaussian surface. Now cavity walls lie inside the Gaussian surface. Therefore, there is no charge on the cavity walls. Hence, the result is proved. Hence, the result B is proved. This was result B. That creation of cavity will not affect the distribution of charge on the actual surface of the conductor. Right? Result C. Let us move to result C. If a charge Q is placed inside the cavity, it will affect the distribution of charge on the distribution of charge Q on the actual surface of the conductor. In other words, a charge of minus q will appear on the cavity walls, and the charge on the actual surface will change from q will change from q to q plus q. Understand this statement. I am saying, let me make a rough diagram here, right? So this is my thread, this is my lump of copper, so there is cavity, right? So here charge was q on the surface. Now I'm saying if I place here plus q charge inside the cavity, some charged particle, on the cavity walls minus q charge will appear, and the charge on the actual surface of the conductor will change from small q to small q plus capital Q. Now still total charge within the body of the conductor in the isolated conductor is q plus q minus q, that is q. That is the meaning of this statement. If a charge q is placed inside the cavity, it will affect the distribution of charge q on the actual surface of the conductor. Now how it has affected? When I place this q charge, it will pull electrons from the actual surface to the cavity walls. Now the absence of those electrons will create here positive charge equal to capital Q, and on the cavity walls minus Q will appear, right? So placement of this charge inside the cavity is affecting the distribution of charge on the actual surface, and the charge in the cavity walls is created, right? And you must understand this. If you place minus capital Q charge in the cavity, then plus Q will appear on the cavity walls and minus Q will add to the actual surface charge, because then the movement of the electrons will be in opposite direction. In this way, electrons are moving from actual surface to the cavity walls. In that case, if you place minus Q in the cavity, electrons will move from the cavity walls to the actual surface of the conductor, right? So placement of charge in the cavity affects the distribution of charge on the actual surface of the conductor, right? So minus Q will appear on the cavity walls and the charge on the actual surface will change. So we will prove that there will be creation of minus Q charge on the cavity walls. That will prove our result. So proof. So again, this is my thread. Now I have again a lump of copper. So there is charge Q. Now there is cavity. Now inside the cavity, I am placing Q, right? And let me prove my result, then I will modify the diagram. So I am saying consider a Gaussian surface. See how proof goes. This is my Gaussian surface. So consider a Gaussian surface lying inside the body of the conductor, lying inside the body of the conductor and enclosing the cavity. When it encloses the cavity, it encloses the cavity walls. Is understood. Consider a Gaussian surface lying inside the body of the conductor and enclosing the cavity. Now what? What is next? Applying Gauss's law. Applying Gauss's law is 0 inside the conductor, right? As we know it from our previous results. Applying Gauss's law, closed integral E dot dA is Qn by epsilon naught. Flux is 0. No electric line of force is passing through my Gaussian surface. So charge inside the Gaussian surface is 0. Therefore, there is no net charge in the Gaussian surface. There is no net charge in the Gaussian surface. Then I move this from the here to here, but there is a charge Q inside the cavity. Therefore, there must be charge minus Q on the cavity walls. The charge inside the Gaussian surface is 0. Plus Q is inside the cavity. Therefore, there must be minus Q charge. Let me use here black color. Minus Q charge on the cavity walls. In order to make the net charge inside the Gaussian surface 0, Q minus Q will then become 0. But where from it will come? If I write only minus Q on the cavity wall, then the charge in the isolated conductor will change from Q to Q minus capital Q. But that is not true. Actually, movement of electrons has taken place. So plus Q will add to the charge on the surface in order to make total charge in the isolated conductor small q, right? Minus Q charge, there must be the charge minus Q on the cavity walls, and hence the charge on the actual surface must change from Q to Q plus Q as the conductor is isolated. Hence, the result C is proved. Let me see. This was result C. If a charge Q is placed inside the cavity, it will affect the distribution of charge Q on the actual surface of the conductor. In other words, if a charge minus Q will appear on the cavity walls, and the charge on the actual surface will change from Q to Q plus Q. So we have proved this result. We've showed minus Q will appear on the cavity walls and charge on the outer surface will change from small q to small q plus capital Q. This was result C. Now I have another result. result D. Now we want to find the external electric field. We want to find the external electric field, right? Now, if let me summarize my results. Now, if I have an isolated conductor, if I place some excess charge, positive or negative, we are taking the case of positive. For example, Q charge, it will lie on the outside surface. None of it will be found within the body of the conductor. Then we said, if we create a cavity, right, this charge is not going to affect. It will remain wherever it is, the way it is, right? Then we said, if I place a charge, keep some charge in the cavity, for example, Q, this charge will change, right? Minus Q charge will appear on the cavity walls. Here, plus Q will add. That means this charge, it will have no more charge, no more positive charge on the actual surface, right? The question is, what about the electric field inside the body of the conductor? We know it is zero. There are no internal currents. What about the field outside? Now you need to remember, if my isolated conductor is of spherical shape, then the charge on the outside surface distributes uniformly. I repeat, for a spherical conductor, rho, that is surface charge density, is constant. So if I have a spherical isolated conductor and I put some charge on it, that charge will go to the outer surface and that will be distributed uniformly over the surface. That means surface charge density will be constant over the surface. But if it is of non-spherical shape, then sigma charge will be distributed over the surface. There will be no charge inside the body, but sigma is not constant in non-spherical conductor. Sigma will vary. And there is another proof, we will not prove that here, that near pointed regions, sigma will be large, near flatter regions, sigma will be small, right? I repeat, the surface charge density near pointed regions will be large, and the surface charge density near flatter regions will be small. Now we will show, if there is some sigma, some surface charge density at certain point, we want to find what is the electric field just outside that point in an isolated conductor, right? So idea is like this. I have an lump of copper again. Now it has some positive charge, right? Some positive charge, right? Let that be Q. Now select certain point P, some point P here, where sigma is, where surface charge density is sigma. So sigma is my surface charge density at point P. I want to find electric field just outside this. Now E inside we know is 0, right? So for that, what we do, clean. Here we know E is 0. We want electric field just outside the body of the conductor. at point P, where surface charge density is sigma. For that, we take a Gaussian surface. Let me use this color. So I take a Gaussian surface like this, cylindrical in shape. This is my cylindrical Gaussian surface. This is my cylindrical Gaussian surface. So consider a cylindrical Gaussian surface piercing the actual surface of the isolated charged conductor, at point P. Let A be its area of cross section. That means this end cap has area A, right? Now there's another thing. When I have an isolated conductor, it has certain charge. You must remember it. Electric field outside the body of this isolated conductor must be perpendicular to the surface. Because if it is not perpendicular, if it is having certain angle with the surface other than 90, like this, then it will have a component. Lying within the body of the conductor, and that will contradict with E is equal to 0 inside the body. So we know there are no internal currents. There is electric field in the electric field inside the body of the conductor is 0. In order to make that consistent with this outside electric field must be perpendicular to the surface. So here electric field is perpendicular to the surface. Therefore, electric field will be somewhat like this. This will be the situation of the electric field outside the body of the conductor, right? That will mean that the electric flux through the surface of my Gaussian surface will be contributed only by this outer end cap. No field inside the body of the conductor, so this end cap will not contribute anything. Cylindrical walls, this curved walls of the cylindrical surface will not contribute anything, only this piece, outer end cap. I hope it is clear to you. Think about it. Applying Gauss's law, closed integral E dot dA is equal to Q inside by epsilon naught. Right, now my flux is, I will split it into 3 parts. Now my flux is E dot dA curved walls plus E dot dA inner end cap plus E dot dA outer end cap, right? Curved walls is 0, inner end cap is 0, only outer end cap is there, and we know E and area vector are parallel. Angle between E and area vector is 0, cos 0 is 1. It will just become EDA. E will be factored out because field over the end cave will be constant. Integral dA will just be A, area of cross section of the Gaussian surface. So it is, I will just write here. Let me use this space. It is here. Let me use this color. 0 plus 0 plus EA. So my flux is just EA. So, well, that is EA. So my left hand side flux is EA. It is Q in by epsilon naught. Also, Q in is what? That is sigma A. Why? Because Q in is the charge inside this Gaussian surface. Now inside this Gaussian surface, only this much area of the surface, A area of the surface will be contained. That area will contain sigma A charge because sigma is the surface charge density. Therefore, EA is sigma A by epsilon naught. Now this A is going to cancel out. So what I get, E is sigma by epsilon naught. This is my result. So if I have an isolated charge conductor, then the electric field outside is perpendicular to the surface. If it is positively charged, it will be outward. If it is negatively charged surface, it will be inward. And field strength will be sigma by epsilon naught, where sigma is the surface charge density there. Now in spherical conductor, sigma throughout is same. Therefore, electric field outside the spherical conductor everywhere will be constant. But in case of non-spherical conductors, sigma varies. We said at pointed region, electric sigma is large, so field outside will be large. At flatter regions, sigma is small, so E there will be small. This completes our applications of Gauss's law. Okay, move to next thing. My next thing is differential form of Gauss's law. Now, we know Gauss's law is written as net flux of the electric field through Gaussian surfaces Q by epsilon naught, right? When we write this way Gauss's law, it is called integral form, as it contains integration, the surface integral on the left hand side. Now, there is another way of writing the Gauss's law, which is called differential form. Now, how we obtain differential from this integral form, that's my topic. Why that is called differential form? Because that basically contains derivatives, that equation, right? Now, we know the divergence theorem. We know we've already discussed it. I will repeat here as I have to use it. We know the divergence theorem. What is that? That says divergence of some vector field, then you show some volume, then let me first write it. You know it in order to remind you. The surfaces. Now, what is V? What is this thing? This is divergence of vector field V. V is some general vector field. What is d tau? It is infinitesimal volume. Infinitesimal volume, right? So actually, there is some volume. That volume is nu. Nu is total volume. Now there is some vector field V existing in this space. Use this color. So in this space in which we are taking this volume, there is some vector field existing. Let me some color. So there is some vector field, V field, right? Now in that space we take volume nu, right? This surface is enclosed by, this volume is enclosed by some surface. That surface we denote by S. Divergence theorem is saying if you take some infinite small volume in this, d tau, then dot that with the divergence of V there, then you take the integral of this whole, this dot product, this product of this divergence and this infinitesimal volume, you add these things over whole volume nu, then it will be equal to the flux of the vector field through the surface S, right? Now what I do, I apply this divergence theorem to my electric field. So I replace V by E, applying this theorem to electric field E, that is replacing V by E, because it is general. Divergence theorem can be used for any vector field. So what we get this divergence of E d tau over some volume is equal to E dot dA over that surface which is enclosing that, right? Divergence of E d tau nu, and here I have flux of E. So this also over some surface, same surface S. Gaussian surface is also a surface, right? Then what I do, now charge inside the closed surface, Gaussian surface is Q. We write it in terms of charge density. Now Q can be written as integral nu rho d tau, where rho is charge density. So it is easy. I have some volume enclosed by certain surface. Now I select a portion of that in order to express the charge inside the surface. I select an infinitesimal volume d tau, then rho charge density, there is rho, the charge density into volume is charge. Then I integrate that over whole volume in order to find the total charge inside the Gaussian surface. Therefore, I will replace this by, first I will use here, let me name this, let this be first, let this be second, and let this be third. Using combining first and second, combining first and second. We get, I will get this divergence of E d tau over volume nu is equal to rho by epsilon naught d tau over volume nu, right? See, I'm saying actually I have a combiner third also. Let me write here. Combining first, second, and third. See how? First is saying this is flux through the surface is Q by epsilon naught. Now third is saying that Q is equal to this, right? And therefore I can write this flux equal to rho by epsilon naught. And my second is saying that divergence is equal to this flux. Got it? That means this divergence, which is equal to this, which from first is equal to this, can be written as this way. So we combined first, replacing this by that integral, charge in terms of the charge density is my second, and second say divergence is equal to the flux. So we got this. We combined these three equations to arrive at this result. Now, since this holds for any volume, this holds for any volume nu, therefore these integrands must be equal. Now these things are integrands. This holds for any volume, therefore the integrands, what is inside the integral, that is integrand, the integrands must be equal. That is, divergence of E must be equal to rho by epsilon naught. This equation is second way of writing the, let me name it 4, differential form of Gauss's law. This 4 is called the differential form of Gauss's law, as it contains divergence and divergence contains derivatives, right? So I will give you now some homework. So question is like this. Let me use this color. Uniformly charged, conducting sphere of 1.22 meter radius has a surface charge density as a surface charge density of 8.13 microcoulomb per meter square. Then part A is find the charge on the sphere, the charge on the sphere. B, what is the total electric flux? What is the total electric flux leaving the surface of the sphere? C, another color. Calculate the electric field. Calculate the electric field at the surface of the sphere. At the surface of the sphere. I repeat the question. A uniformly charged conducting sphere of 1.22 meter radius has a surface charge density of 8.31 microcoulomb per meter square. Part A, find the charge on the sphere. What is the total electric flux leaving the surface of the sphere? Calculate the electric field at the surface of the sphere. And you know 1 microcoulomb is 10⁻⁻⁶ coulomb, right? So this is all for today. Do your homework and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.